You've probably heard the saying that a watched pot never boils. Turns out this isn't just psychological. In the quantum realm, it's actually true. Welcome to one of quantum physics' most mind-bending phenomena, the Quantum Zeno Effect, where simply observing a system can literally freeze it in place. For the next 15 minutes, we're going to unravel how this strange effect works, explore the real experiments that confirmed it, and discover how it might even help us build quantum computers. Stick around. This might change how you think about reality itself. To understand the Quantum Zeno Effect, we need to go way back, about 2,500 years back to ancient Greece. Philosopher Zeno of Elea proposed several paradoxes about motion and time, but the most relevant one is his arrow paradox. Zeno argued that if you look at an arrow in flight at any single instant, it appears motionless. If time is made up of these instants and the arrow isn't moving in any of them, then how does it actually move? The moving arrow should be at rest. For centuries, this was considered a philosophical curiosity resolved by calculus. We know arrows do move, thank goodness. But in the 1970s, physicists Baidyanath Misra and George Sudarshan discovered something remarkable. In the quantum world, Zeno's paradox might not be a paradox at all, it might be real. To understand how this works, we need two key quantum concepts. First, superposition, the idea that quantum systems can exist in multiple states simultaneously. Think of Schrödinger's famous cat, both alive and dead until observed. Second, wavefunction collapse, the idea that measuring a quantum system forces it to choose a state. Now here's the crucial part. In quantum mechanics, measurement doesn't require a conscious observer. Any interaction that distinguishes between states counts as measurement, whether it's a scientist in a lab or a photon hitting a detector. The mathematics shows us why frequent measurement matters. For very short times, the probability that a system remains in its initial state decreases as the square of the time. If we measure frequently enough, we can keep resetting this probability curve, effectively freezing the system in place. The theory was compelling, but did it actually work? In 1990, physicist David Wineland and his team at NIST decided to test it. They used laser-cooled beryllium ions trapped in an electromagnetic field. By applying precisely tuned radio waves, they could cause electrons to oscillate between energy levels. Then came the clever part. They flashed these atoms with laser pulses that effectively asked which state they were in. Just as predicted, when they made these measurements frequently enough, the electrons stopped transitioning between states. The quantum arrow was frozen. This was one of the first experimental confirmations of the Quantum Zeno Effect. Since then, numerous experiments have confirmed the effect in various systems, from suppressing radioactive decay to inhibiting quantum tunneling in ultra-cold atoms. Beyond being a quantum curiosity, the Zeno effect has practical applications. One of the most promising is in quantum computing. Qubits are notoriously fragile, collapsing when disturbed. But by strategically applying the Quantum Zeno effect, we can potentially freeze qubits in their desired states, protecting them from decoherence. Some researchers believe migratory birds might even use a quantum Zeno-like mechanism in magnetoreception, their ability to sense Earth's magnetic field. The effect might help maintain quantum states long enough for navigation. It's also used in commercial atomic magnetometers and has potential applications in quantum sensing and imaging technologies. Now, not everyone agrees on what exactly causes the Quantum Zeno Effect. Some physicists, like Leslie Ballantyne, argue it's not about measurement in the abstract sense, but about the physical perturbation caused by measurement. This isn't just philosophical nitpicking, it leads to a fascinating opposite phenomenon, the Quantum ANTI-Zeno Effect. In certain circumstances, frequent measurements can actually accelerate quantum transitions rather than suppress them. The key factor is the measurement strength and timing. So what does all this mean? The Quantum Zeno Effect blurs the line between observer and observed in a way that challenges our classical intuition about reality. It suggests that at the most fundamental level, the universe might not evolve independently of how we look at it. The quantum world seems to demand participation rather than passive observation. What do you think? Does this mean consciousness plays a role in quantum mechanics, or is it all about physical interactions? Let us know in the comments below. If you enjoyed this deep dive into quantum weirdness, hit that like button and subscribe for more content exploring the frontiers of physics. Thanks for watching, and remember, in the quantum world, keep your eyes open. You might just freeze reality in its tracks.